How can key characteristics of quadratic functions be used with projectiles in motion and to find area of shaded regions? We'll go over areas of shaded regions at the end. Projectiles in motion, that's like throwing something. So like, woo! Projectile in motion. Okay? So, for example, here's the first example. This is a baseball. This is the graph of the height of a baseball after it gets hit. So you have a batter, the pitch is thrown, and they hit the ball, right? So what are the different parts? So the zeros, where they are specifically going to represent only when it hits the ground, because realistically, this part of the quadratic equation or the parabola here didn't actually happen. We can use the quadratic to model it over this domain from 0 to here, whatever number this would be, and that represents the time, right? So my zeros, this right here, is when the ball hits the ground. So we could tell how long it took after the ball was hit till it hit the ground. That'd be your zeros. Your y-intercept is going to be the height when the ball was hit. So when the bat hits the ball, that's going to be your y-intercept right here. Your vertex represents the highest point, specifically two things. It's going to represent your y-coordinate tells you how high the ball got, and your x-coordinate tells you what time after it was hit. So how long did it take to get there? It's generally how you use the key characteristics of quadratics within these projectiles. In this case, this launch projectile was a ball being hit by a bat. In this case, this is a quarterback throwing a football. And you can use these key characteristics to tell a couple things, like how high did the ball go? Well, here's time and here's height. So here's 6, 7, 8. So it looks like the ball got to about 8 feet in the air. And it took it about, and these are seconds, so it took about 1.5 seconds. So 1.5 seconds is how long it took to get there. The height here of the quarterback who threw the ball, how tall, how high was the ball when it was released? Generally, it might be probably a little bit above the quarterback's head, depending on their mechanics, right? But it looks like it was right about 6 feet. So the ball was released at 6 feet. It went up to 8 feet, and then it went all the way down to the ground. So it hit the ground after about 4.5 seconds. It was in the air from 0, so it was in the air for 4.5 seconds. It took 1.5 seconds to get to its height. It started at 6 feet, it ended on the ground. This part really isn't needed. It's just part of a quadratic. But in terms of analyzing this situation, really only look from 0 to 4.5 here, and don't really worry about anything else. But again, that's just how you can use these key characteristics to analyze and look at actual projectiles and things. Now, talked about shaded regions. So this is something you've probably seen before in math, where you have these rectangles and you have to figure out the area of just the shaded region. So if this outside rectangle is 5 by 10 units, you do 5 times 10 and you get 50. And that's the whole area of both rectangles. So then you take away the inside rectangle. So 2 times 6 is 12. So 50 minus 12 is going to be 38. And so the shaded region would be 38. Now, how does it apply to quadratics? Well, sometimes we have situations where we're changing the numbers around, or we have variable numbers. So we might have a garden that we haven't quite decided on, but we do know we want a 2-foot path around the outside, right? So we would kind of like put this path here. This is 2 feet all the way around the outside. And this is probably like some kind of problem you might see on a test. You might see a problem like this on a test where they say, here's the garden, here's the dimensions. The width is 2x plus 1, and the length is x plus 3. What's the area of the garden path that extends 2 feet beyond it? So you got to kind of use a lot of thinking here. First, I would draw the picture here. We add on these 2 feet, and then you basically have to say, okay, this is 2, and this is 2. So I basically have to take this 2x plus 1, and I have to add 4 to it. So this is going to be 2x plus 1, and I have to add this, and it'll give me this whole side here. Plus 2 plus 2. And you do the same thing here for the length. X plus 3 plus this 2 up here and this 2 down here. Plus 2 plus 2. So we can add that all together. And we get, what, 2x plus 5. And then x plus 3 plus 2 plus 2. So 2, 4, x plus 7. Now, I have to go through the process of multiplying. And I didn't bring a blank board in here. X plus 7 times 2x plus 5. I have to multiply that together to get the area of the whole thing. X plus 7 times 2x plus 5. So these now look like factors of a quadratic, right? I can multiply them together. X plus 2x is 2x squared. X times 5, or x times 2x. X times 5 is 5x. 7 times 2x is 14x. 7 times 5 is 35. I can combine like terms. 2x squared plus 19x plus 35. That is the area of the entire garden, including the path. Now I have to find the area of just the garden and take that away to figure out the area of the path. This is like a legit problem you might want to work out, because if you're buying concrete, a lot of times you have to buy it by the cubic foot. So if you're buying, or by the square foot or something, so figuring out the area is going to be a key step in that. Area of just the path. All right, so now I would subtract from this. I have to do these two factors of, what is it? 2x plus 1 and times x plus 3. So minus, and then in here I do 2x plus 1 times x plus 3. You could do area model to multiply these together. 2x times x is going to be 2x squared. 2x times 3 is going to be 6x. 2x, no, doing that. 1 times x is going to be x, and 1 times 3 is going to be 3. Now, I can combine like terms. 2x plus 7x plus 3. This is all being subtracted, so I have to distribute the negative. Minus 2x minus 7x minus 3, 2x squared, sorry. And I'm doing 2x squared plus 19x plus 35. 2x squared plus 19x plus 35. I can now combine all these terms. 2x squared minus 2x squared, that cancels out. That was easy. 19x minus 7x is 12x. 35 minus 3 is 32. So it ends up just being a linear equation. And that's how you would use that to figure out the area of a shaded region. How can key characteristics of quadratic functions be used with projectiles in motion and to find the area of shaded regions? Here's one more projectile in motion.